Hello, welcome back to MAD, Minds Against Dogma.
Welcome back, and today we're going to walk on the dark side.
Yeah, I feel like I want to interview
on the
you.
dark side.
I want to interview you today because I read your book, and what I love about it is I love that you simplified it for the layman, and you just cut the fat out of it, and you just talked about the problems, the possibilities. Spoke a little bit about simulation theory that I'm always fascinated about, and they say the idea about a god, basically, or something. Okay, we'll slow down. Something that's fine tuning everything, the fine tuning aspect of the simulation theory, right? And I'd be curious to ask you later on how you feel about that in a moment. But I want to talk about your book because you hear a lot about dark energy lately, and people are very confused about it. They confuse dark energy with dark matter. They confuse the field or space with dark matter or dark energy. And it's very confusing, I think, to many people. And people talk about it like they know what they're talking about. And after reading your book, I realized no one knows what they're talking about. and after reading your book, it left me with despair and hope at the same time. The despair was that we really don't know what's going on. Right when we think we have all the formulas and the math to kind of get a sense of how reality works at the quantum level, right? And the macro and micro level, right? Like, suddenly something's discovered, and it's like throwing a mathematical wrench into everything we know. And it feels like you have to go back to the drawing board to reimagine what is happening, because it just doesn't make any sense. It goes against everything we know. We can send a rocket to the moon. We can send satellites through space with cameras, all based on the formulas we already know. So it looks like we got it, pretty down, right? We got it down, right? We can do all this stuff. We proved it. We just like Newtonian physics. We can fly airplanes and stuff, all this wonderful stuff, right? And then there's a discovery that's made out in the further reaches of the universe. And then, of course, right here, eventually, that throws everything out of whack, that says that this can't be the math we're using. So tell me in your, for laymen, tell me in your words, what would you like to talk about today? Dark energy and dark matter. And before you start, could you just sum up the two, just so we know that we'll get to the other one on another podcast?
Right. So first, I just want to mention that if anyone is interested in the book, it's a rapid read. It's called The Dark Side of the Universe, and you can find it on Amazon. It was published in 2015 in collaboration with Clive Prince, who is one of the co-authors of The Forbidden Universe, among many other books. And it's part of a series called The Unexplained. So you can read more rapid reads on different topics. This one is on dark matter and dark energy and overall the dark side of the universe. So I would like to go with dark matter first, but to differentiate between the two. So dark matter is actually matter. Dark energy is not matter. So
I noticed in your book, I thought they were related. They're completely unrelated, right?
No,
They could be, right?
They're again, as I say in the book, when I talk about whether they're related, I say it doesn't appear to be so. But when you're talking about such big unknowns, it's best never to say never.
Yeah.
In the current theories and models, they're not related.
They're not related, even though they're saying dark matter and dark energy. So yes. I think the layman, or anyone for that matter, who has heard about dark energy would assume that like the dark matter creates dark energy, or dark energy is affecting dark matter or something. But they're two different things as of now, as far as we know. It could be correlated, but as far as we know, they're two different things.
They're two different things, and it's not like dark matter creates the dark energy. Again, I understand the misconception because of the nomenclature that is dark for both of them, but they describe two very different things. So again, dark matter is matter that we cannot see because it does not emit, absorb, diffuse with like light. So
say that again. It does not
absorb, emit, reflect light or any other form of radiation as we measure it. So like electromagnetic radiation or radiation in any of the known spectra. So that's why it's called dark.
So if it doesn't do that, we know it exists because of gravitational pull, like a gravitational lensing, right? What's the term?
Right. The way we let me first differentiate between the two, and then I'm going to come back and say how we know that there's something that we can't see that exists, right? The dark energy, on the other hand, is this energy that's correlated with the expansion of the universe. It doesn't bring things together as the force of the dark matter would actually. It actually pulls things apart. And it's a negative type of energy, if you want, from that perspective. Now, they do both of them. When you think about the density in the universe, both of them have a certain contribution. That's why we say that 70% of the density of the universe is actually dark energy, while 85% of the matter of the universe and only close to 30%, 26 point something % of the density is dark matter. Now, coming back to dark matter. So let's take them one at a time, because again, I don't want people to have again, that I don't want to spread again this confusion about dark matter and dark energy being in the same boat.
Great. So we put dark energy on the side for now. We
put it on the side.
It's a pulling away as opposed to gravity, a pulling in. So it's a kind of a pushing out energy. We'll deal with that next. Okay.
And it's not the energy created by dark matter.
Right. It has nothing to do with it's just this energy that is strange because it's going against the gravitational pull, and we don't know why it's happening. And there's some suspicions, and we'll talk about that on the next podcast.
And again, it's dark because it's not one of the energies that we know
that we can measure
like radiation correlated energy.
Got it.
So and it doesn't have to do with the things we see, like a kinetic type of an energy, for example. So that's why it's called dark. Now, it's true that people have proposed other names for dark matter. One of them, we laugh about this in the book, that we should have probably called it occult in the original meaning of the word, which is hidden matter, but that was just asking for trouble, or ghost matter. Because if it was actually dark in the dictionary definition of the word dark, we would be able to see it. Because darkness would actually block the light from coming, while dark matter is more like transparent and is not actually blocking the light.
Say that again.
It's not dark matter. Dark matter is not actually blocking the light as darkness would.
Oh, see, when you say it doesn't reflect, I was under the assumption of absorbing, but you're saying it doesn't
absorb it either.
It's some kind of transparent energy.
Right.
That doesn't get affected by light or radiation, pretty much.
And it doesn't emit light or radiation either. So that's why the only way, and this comes to your question at the beginning, like how the dark do we know that it exists, right? A series of ironies. So to do a little bit of like history of science here, because I think it's funny of how these things came to be, and it goes with the mind against dogma paradigm. So in the 30s, most of the people were actually pretty sure, as you said, that we know what's going on. We know what's going on out there. We can, as you said, calculate at least what the rocket should be able to do if they were to fly, and how the universe is forming and all that, just by looking at one galaxy, basically. And what happened was, and again, that was already after a bit of a war in the scientific community that had to do with the steady state universe and Einstein theory of relativity and all that. But then people were looking at what's going on, and they realized that no, it's actually something more than the steady state universe. Things are moving in the universe as they wouldn't if we were in a steady state universe.
And
Now,
you saw that by why? Galaxies are getting further apart. They measure that.
right.
Okay.
Right.
Right.
So, but that's connected to the dark energy side.
Got it.
For now, we're going to pause here where the things were a little bit in a shake-up kind of a state, you know. There was already a transition from the steady state universe. So what happened was Zwicky, who was a Swiss astronomer and quite a character, I might add, looked at the clusters of galaxies. So measuring the way galaxies move within a cluster, which is again a structure in itself. So a cluster of galaxies is considered to be gravitationally bound by the galaxies inside of it. So you can basically take it out of the universe and sort of study it as its own object. So looking at the cluster of galaxies, he measured the velocities of the galaxies inside. And they were not explained by the mass that he would observe, by the matter that he would observe, by the luminous matter, because that's what we observe. We observe matter that emits light. So it was like it was a lot of matter that we wouldn't see. And he coined this term that he allegedly wasn't happy with. The German for dark matter was dunkle Materie, which means dark matter. And he wasn't taken very seriously with that, especially because the character that he used to call his peers spherical bastards, in the sense that no matter which way you look at them, they're still bastards. So he had a way of naming things. So it wasn't taken very seriously back then. Now, fast forward almost like 40 years. People started to look at the way galaxies rotate. Now, within those 40 years, from the point of view of history of science, another thing happened, a shift in between the steady state universe that I was mentioning before and the Big Bang. And ironically, the Big Bang was first proposed by Lemaitre, who's the one that actually talked about the Hubble constant before Hubble talked about what we call now Hubble constant. He was a Belgian priest, Catholic priest, who wasn't taken seriously from all other reasons, but because he was sort of open-minded to the idea, at least, again, ironically, that the universe may have a beginning, a middle, and an end. He would interpret the observation that's showing that the universe is actually evolving, is not in steady quasi-equilibrium state.
And how do you come up with that? Just by
looking at how the light in the universe travels and how the galaxies move and all that. It's explained by this parameter that seemed to be a constant, and yet another constant in the universe, showing that it has a certain evolution. It was more than the math made sense. It was also a way of like organically explaining what he was seeing. And he called it the fireworks universe, which the fireworks universe, the fireworks. because it seemed like it was starting from point, huge expansion, like an explosion, and then reaching a point in which gravity kind of catches up with the initial expansion, and we have the state that
Is that why before, I want to get ahead of ourselves, is that why before dark energy was discovered, they thought that after the universe expanded, it would eventually contract again back into its, because the gravitational pull will catch up on itself, right? And then eventually start pulling everything back. And that's what they used to think. And then is that
the heat death? Yes.
Okay, got it. All right.
Yeah. Or the big crunch. Well, the heat death is actually the heat death would be that the universe is expanding to the point of which gravity can hold things together. And the big crunch is basically when gravity pulls everything back and contracts upon itself.
That's what they used to think until they discovered dark energy. Okay, good. All right. So we're good. All right.
So Fred Hoyle, actually, interestingly enough, as a put down, called the model the Big Bang, because he was one of the steady state universe people. And it's the ironies here are the people who were trying to put down one theory came up with the name that will actually follow around that theory, you know.
Oh, interesting. So who came up with that name?
So Fred Hoyle is a British astronomer. So he was one of the steady state universe people, and he called it the Big Bang. Like he called Lemaitre's theory the fireworks, the Big Bang, and ended up being the one.
Cool trivia. That's cool.
That's instant karma. Being the one that actually coined the name, and forever, you know, in the history of science, being the one who named the thing that he did not believe existed.
Yeah. Isn't that
so that's the Big Bang. That's dark matter, you know. So it's yeah. Be careful how you name things in science. So okay, so that was already changing. Like people would believe that there's actually a beginning, a middle, and there was such a thing as a Big Bang, and know that the universe is not in a steady state. And what happened was people were looking, and this is like Vera Rubin's work. They would be looking at the rotation curves of galaxies, and before you jump on like, wait, what curve of galaxies? So when galaxies rotate, so they rotate in the center, like it would be a rigid body, like a record, like it's solid. So you know how record rotates. This is like the center of the galaxy. Again, it's an approximation, but it's closer to like it's so concentrated the matter that it looks like it's solid. Even though you have planets and stars and dust and other things, it looks, because of the gravitational pull and the concentration of matter, it looks like it's almost solid, the rotation. Now, when you go further away from that radius where things are still working like it's a solid disk, when you go further away, the further you go, it starts rotating like it's more like a fluid. Like if you would drop a pebble in water, and you know, you have one circle here, and
circles,
and the further you go, the circles become less and less defined. And if you were like to stir the water, you would have this kind of like fluid like follow up until you go further and further, and there's no such thing. So you can imagine that the further you go in the outskirts of the galaxies, at some point, there would be like a galaxy that doesn't have enough velocity to be pulled in this orbit, would just fly past it. So that velocity can be estimated. Like, what's the escape? We call it the escape velocity. The velocity that you had this gravitational pull inside, which is the disk plus this outskirt area of influence that drops with the distance. What's the velocity for which, if you are above that velocity, you're going bye-bye? You say hello to the galaxy and off you go. You're not trapped by the gravitational pull inside.
So one galaxy is here, another galaxy is passing.
No, of a star, a planet, something small. Think about
she's a
something small.
galaxy. Okay. So you got a body, right? Or a heavenly body flying by, and here's the galaxy, right? A planet, right? And you're saying that what's the speed of this planet that would be fast enough to not be pulled into the gravitational pull of that galaxy or the edges there, right?
Right.
Okay,
So that's called the escape velocity. Because again, if you're close to the center, you're like on the record. If you're a little bit outside, it's like you see those spirals. You're a planet and you're still orbiting, depending on where you are. At some point.
So normally planets would get sucked in at a certain speed and add to that tail, if you will, at the edge of it.
Right.
Okay.
Exactly, because of the gravitational pull from inside. So that velocity, that is the limit of either being inside, orbiting around, rotating with the galaxy, or going past it. It's something that you can estimate based on whatever matter you have inside. And the whatever matter you had inside was the matter that was with your telescope, basically the luminous matter, the one that you saw.
Got it.
So they estimated that velocity. And lo and behold, it was much smaller than what they were actually measuring. So they calculated from the mass inside what's the escape velocity. And yet, there were things moving around the galaxy with a much higher velocity.
They still got sucked into it. They still didn't escape.
Exactly. Much higher. Much higher.
So you're saying that these things that were moving so fast should have easily just went right past it. And for some reason, it was still pulled into the gravitational pull. But yet, then they measure what the potential gravitational pull would be, which is measured by the speed, the speed in which it can, whatever you just called it. What'd you call it?
The gravitational pull was measured by the mass that you would see.
The mass.
That matter.
Gotcha.
Yeah.
So they can kind of get a sense of the mass and then know the speed. And yet, things that were passing by, right, that really that going very fast, they should have just went right through, got sucked into it.
Right.
Into its pull.
As if it was way
denser than they thought.
Way more matter there that they couldn't see. But again, way more. Like Rubin's first estimation was 6 times more. And we know that that's an underestimation.
Conservative, really.
So way more matter that they couldn't see. As if there was this kind of like whole halo keeping things together from outside. This whole halo of matter not allowing things to escape for such high velocities. And that's why they were, again, coming back to the idea that it's called dark matter because we don't see it. It's a lot of it. And this was not happening for one galaxy. Because you can say, okay, well, maybe this galaxy is different because, I don't know, some other processes that were taking place inside of it. That was for most galaxies. This type of huge difference in the estimation of what the gravitational pull should be from the mass that we see and what it actually is when we look at the velocities and the escape velocities. So this is how the whole thing started. In order to explain the rotation curves, this is a rotation curve. So you would basically look at the rotation velocities with distance if you were to plot it. When looking at these rotation curves for most galaxies, they cannot be explained by the matter we see inside of it. And we're not talking a factor of 1, 2, 3. We're talking like 10 times more in certain galaxies. So the first explanation for that would be, okay, there's a lot of matter there that we just can't see. What can it be? Well, the most obvious, like the first candidate would be dust. Galactic, intergalactic dust. We know that there's some out there. So that maybe it's the explanation. Now, for the fans of His Dark Material, which is a new series, I don't know if you know about it. It's a series inspired by inspired by the book of Philip Pullman. The title is funny because it's actually taken from Milton's Paradise Lost, when Satan, the character, says, unless the Almighty Maker ordain his dark materials to create new worlds. His dark materials being basically the dark army of the Almighty Maker. Now, in that TV series, the dark matter is this magical dust. So now, for the fans of that TV show, myself included, because it has a couple of other things that are really funny and really, really cool to watch, I can tell you it's not dust. Doesn't matter how magical it is, because dust has other properties. Like, remember when I told you at the beginning that it's dark, but not in the sense of like blocking the light? Well, dust does that. And other things that dust does, we can reflect at some point some light of dust if you have certain type of phenomena next to it.
And it doesn't do that.
And it doesn't do that either. And the more we studied other things, like, for example, the cosmic microwave background, which is this radiation coming from the decoupling era, which is like 300,000 years after in between 100,000 and 300,000 years after the Big Bang. We call it the radiation from the Big Bang, but it's not that. It's when the matter that we do have now in the universe decouples from the primordial soup, if you will. So this radiation that we measure now, and a couple of other experiments that look at the ratios of elements in the universe, all points out that this regular matter, we call it ordinary. I don't know why, because it's only 5% when you think about it. In the density, or like in below that is 15 in the matter. So this is like the regular matter that we call it regular. Is not enough to account for the vastness of dark matter. So there are now more than just one reason to look at dark matter. There are a couple of things that it's like a puzzle that if you put all the pieces together, they point towards dark matter being this type of particle that we don't know yet, we haven't detected yet, and that doesn't do what other particles do. Does not interact with other particles, except maybe very weakly. It doesn't do any of the electricity, magnetism, because it's neutral in the sense that it doesn't have a charge. And it only interacts gravitationally. So we can only see it gravitationally. And here are a couple of models that we can talk about. But the majority of scientists now believe that this is a different type of particle that is not formed of particles that we do not know of. It's something entirely different, and it's very hard to detect because, again, you detect radiation. Doesn't do that. You detect the interaction with other particles. No luck there either. So we had it inferred from its gravitational effect on the formation and evolution and structure of galaxies. But for now, that's about it. Now, this is not to say that it's undefined. And again, there were physicists who I had this experience recently where I kept saying it is defined. It's not undefined. It's undetected. I said it 3 times, and again, the whole deletion, distortion, and generalization. If someone wants to believe that it's just this fluke that the physicists came up with, that's not going to change. So once again, it is defined, as I said. It's dark matter that does not absorb, reflects, emits light, or any other known form of radiation. It only interacts gravitationally, and we see its effects at the level of the galaxies. And that's the definition of the dark matter. Now, there are people who say BS. That's just you not knowing enough about the laws of physics in the universe. That velocity estimated by this gravitational, you just miss something there. Acceleration at a certain scale. It doesn't work like we know in the macroscopic Newtonian world on Earth. Or gravity does funny things when it wants to. Or
what do you say to that? Those two.
So I say that, again, because of the evidence we have being from different parts, if you want to have a competing theory, you have to explain, again, all those different things, not just one. So, for example, MOND as a theory is called modified Newtonian dynamics, which basically said that a certain scale of the galactic scales, the Newtonian dynamics, the whole picture is different.
It's like the quantum world. It's like the quantum world, and they change based on the density or
right. Again, like a different phase. Right. Still in the macroscopic world, but a different phase that we didn't know of because we never dealt with those numbers for acceleration and so on. Got it. So that actually, MOND, when it comes to the galaxy picture, it explains pretty well the picture. But remember, and I actually started, I won't be I can't be thought of as biased here because my dark matter endeavor started with MOND. So I actually started the whole dark matter research by working in MOND. But then I realized that there is evidence that MOND cannot explain. That can so far has only been explained by this type of a different type of particle. So to have a competing theory, it has to explain all these kind of discrepancies. And those alternative theories, while they explain one, they don't deal with all the others. Now, having said that, I'm also not one to believe that there's only one very simple, very economic explanation for how things are. So I wouldn't be surprised if there's something in both these fields that sound like like competing and incompatible. So it may be that to some extent, our laws of physics, the understanding of our laws of physics is not complete at those scales. And throw on top of that dark matter just because, for the complication's sake.
Well, that adds to simulation theory a little bit, doesn't it? That it's just perfect. Everything was so perfectly fine-tuned that over there we need gravity to act differently than we do to have gravity work here because it's so finely tuned. So it just gravity's programmed in a different way outside of our galaxy because we need gravity programmed a certain way here. And that would actually make sense, right? It would actually support simulation theory, wouldn't it? To some extent.
So again, that's the other explanation. That's completely, it's in the all bets are off because if we live in a simulation and the programmers need dark matter for things to be as they are, for us to be their things, then you cannot really argue with that either way. It is because we need it. But make no mistake, this is not really different than the religions we.
Yes.
Just this is another. This is another God's paradigm. I know many physicists are going to be upset about this statement. I don't care. It's exactly as it is. It's just because it's cool now to say we live in a simulation, as opposed to we have these angry, sometimes gods that made the universe in 7 days and whatnot. Okay, I can see the difference in its absolute. But when you scale things, that's just another God-like view of the universe. There's no difference there. And if you look at it, like if you look at how the simulation theory basically explains itself, is within the same dogma. It's as it is, We needed it, therefore it is. The programmers needed dark matter, therefore dark matter is. It's exactly that type of explanation. Now, personally, and knowing programmers as I do, that would explain the mess. So simulation theory would totally explain the mess in the universe and how irrational it is. But leaving that aside, that's no different than saying there is this God that's outside of us that created the universe such that when you really think about it, again, it's scaled, and from the perspective of like behavioral science and the perspective of the other things that we talked about, of how you create a dogma and what the psyche does, it is created in a manner in which it's scaled with the times. Like, it would make sense now for scientists to say you live in the simulation universe with all the matrix-like things and all the like digital view of the world and all those things. As it did make sense, guess what? For the people back then to create a god that was doing all these things. It's just the problem has been scaled. It's not a significant difference in between how you look at these things.
Right, and more stories were thrown into it, stories and ideas and metaphors of why God did that or that, rather than the fact that there's something that's programming everything for whatever reason. So the difference between simulation theory and basically, let's just say the Bible, right, is that they gave that programmer, personality. They projected human traits onto it. It was mad, it was angry, but it was still this idea that there was something that was bigger than us programming everything around us and through us. And but I think that's why people have this aversion to it, because as soon as you say, well, there was a creator, then you go right to your experience of what you were told God was, and based on your religion, and you might have had a problem with that, and then you're conflating the two rather than just a giant programming thing. As opposed to a programming thing that has all this anger, personality, and judgment, and caring about what you're doing with your clothes off in your bedroom.
Well, but see, that's what I'm talking about when I say that the whole problem is scaled, because back then that was the interest, right? And those were the taboos, and people would need to have that thing projected, like their personalities and the face and all that. Now, think about what is our reality nowadays. How much are we in front of a computer? How much we program things with a computer? How much the computer is a part of our reality, and project that. It's basically the same sort of a thing. Because you wouldn't say for now, and again, simulation theory has many different interpretations. Like, are programmers like really like in our image, or is that thing like is a computer in its image, again, in the computer's image, or is like us from the future, as if that would somehow solve all the religious arguments. So is like a ramification there, as it is in all the religions, because that's also like a different view in depending on the religion. But when you think about it, it's again the projection of our reality and the thing that we do most, which is computers, programs.
Okay, got it. I have a question and a comment. Okay, my question is: at CERN, were they looking for dark matter?
Yes.
Did they find anything that suggests
no? But here would be a good time to actually differentiate within the dark matter as a particle, because as I said, there are alternative theories to dark matter being an actual particle. But if we consider dark matter to be a dark particle that we just haven't detected yet, there are different theories. And now, again, none of these has been proven to be right. Some of them have been proven to be wrong, in the sense that they do not fit. The more you look into them, they do not fit what we observe. But if I was to make a classification, it would be cold, warm, and hot. Now, cold dark matter is a particle that's very heavy, cold, and slow moving. Hot dark matter would be something that is light, it's fast, and it's hot. So in all this, like, changing climates, we're actually going to categorize them by the hotness, but this is exactly where things get heated, and this is a pun intended. Because in the middle, there are these like 50 shades of warmness, if you want, where everything from a mega electron volts to an electron volts, a large range of energies, you can call that warm dark matter. Now, within each of these categories, scientists have hypothesized, theoretically, different types of candidates. And here the names are, again, like for anime characters, Neutralino, Axino, Axion, Gravitino, Q-balls. That's an oddball name for a particle, but we have Q-balls as well. The main category would be basically for the cold dark matter. It's called WIMP.
What's it called? WIMPs, right? Remember that for your book, right? WIMPs.
Yeah, it stands for weak interactive massive particles. Because you see, as at the beginning, I said it doesn't interact with matter, but that would be a no-go for detection. So then scientists said, oh, maybe it does a little bit. Because otherwise, how would we detect it with a detector? So maybe it does just a little bit. Once in a blue moon, it does interact weakly with a particle, and we would be able to see its effect. And those are called WIMPs. And again, the opposite was machos, because macho would be massive objects, but made from ordinary matter. And we know that, again, that's not the case. So they're not like massive objects made from ordinary matter that somehow are just dark because we don't see them because the matter is not luminous enough and all that. So in the cold dark matter, we have these WIMPs, the weak interactive massive particles. Then a couple of them in the warm dark matter, and neutrinos are hot dark matter. Again, ironically enough, there is such a particle from the whole dark matter conundrum that has been detected. Those are neutrinos.
Neutrinos, right? And
Yes.
I remember reading about that where that's why they go through things, so that like they're actually passing through matter, right, or something like that.
Yes,
Right? I
yes.
remember years ago.
Very...
Yeah, I didn't know that was dark matter. That's cool. That's cool to know that neutrinos are.
It is dark matter in the sense of its definition, because they don't absorb emit and all that. But because they're so hot and fast, they don't settle down to form a galaxy. Within the age of the universe, they wouldn't be forming one galaxy. So they can't make up the dark matter contents that we're missing. We need something that's heavier and slower in order to form galaxies, because you have to kind of get things together and quite early in the universe to account for what we observe. Neutrinos are just flying by. My first simulation was actually done with something very hot. I waited for, again, ironically, 7 days, and nothing happened. It was my perfect universe. 7 days, nothing happened. The particle was too hot to create even one galaxy. One settled down to form one. It was just fast and furious. Now, why do I bring into discussion the simulations? Because since we can't actually play with it because we don't have dark matter, and the only thing we can do is infer its existence through observations, what we do is simulate.
So you're not really working with some hot, fast neutrino, basically. You're simulating in a computer.
Right. We're simulating particles in a computer. We give them sort of the same properties in the sense that we allow them to act gravitationally and nothing else.
Yeah, nothing else.
We put them on a certain distribution as random as possible, redshift 100, and by redshift 100 means very early in the universe. And we let them interact gravitationally until they form filaments and galaxies and structures. And then we compare that with what's observed. Now, cold dark matter, as it were, which is very simple to simulate.
So let me jump in. Is the reason why you started recognizing that there was cold and hot is because you understood there was a hot, but if that can't create the universe, then maybe there has to be a cold dark matter, because that would have more maybe gravitational pull, heaviness, more consistency. Is that what the theory was? Is that why you decided, or physicists decided, that there was a cold dark matter as well as a hot dark matter?
Right. So that's one of the reasons. But there's another reason. You see, in terms of how particles are produced, you need to come up with a theory that's consistent, that allows for the other particle to be produced, the ones that you measure as well. So you need to have, again, this theory that allows for this dark matter particle to be produced and do these cool things, or cool as being the operative word here, and all these other particles, neutrinos and neutrons and protons and electrons and photons and all that. So people were looking at what type of theory would be doing both. Because in the standard model, we know how these other particles are produced and why they have what they have, the charge that they have, and this number of quarks and all that. So people were looking at what they called extensions of the standard model. And one of them is the supersymmetric model. And a cold dark matter candidate came out naturally out of that model. And I say naturally because, again, it's a model theorized. So it's not like it's a direct proven empirical consequence of that. So cold dark matter was a candidate that solved this problem of the dark matter, plus a couple of other things that the theories were still struggling with.
Through a simulation, it showed that the heavy dark.
So this is theory. This is theory that I'm talking about. Axion, because I told you that there are a couple of different models for each of these particles. All I'm talking is like hypothetical models. Another one, the axion, that was solving some other things that the theorists were struggling with at the particle level, and had sort of the energy to explain the dark matter. So it was a twofold approach here. They needed one type of particle that would explain, as shown by simulations, the observations, and also come out from a particle physics standpoint, from a theory that makes sense mathematically. So what we did was taking this hypothesized particle, putting them in a simulation, and see if the outcome matches what we do observe in the universe, like how galaxies are distributed, when they form, how they rotate, how many are there, and so on and so forth. What's their internal structure, those rotation curves and whatnot. And for the longest time, the cold dark matter simulations were matching pretty well what we saw in the universe. Now, the more observations were done at the level of the galaxies and inside the galaxies, there were 2 points initially that people were not still puzzled about. The very central internal structure of galaxies was not in agreement with what you would see in the simulations of cold dark matter. And then the number of satellites, like small galaxies in the Milky Way, for example, or in other galaxies, the number was in disagreement with cold dark matter and the observations. So people said, well, okay, but we're just comparing pure dark matter simulation with galaxies that have all sorts of other matters and black holes and supernovae ejections and all sorts of these other processes. So we can't do that. We can't say, okay, cold dark matter doesn't match that because it's alone. So they started fine-tuning the baryonic physics Baryons are the other type of particles, the ones that we know. Most of them are baryons. And they started putting a little bit of this and a little bit of that in the simulation to try to match what we see in the universe. And there were still things that didn't match. We have a high number of galaxies in the universe that are predominantly dark matter dominated.
So some are more dominant. Interesting. Yeah. So some have more dark matter than others.
Right.
Interesting.
And we call those dwarf galaxies. The number of I think one of them is actually 99% dark matter. Again, by the estimation of 90%.
That almost sounds like you're measuring a black hole. If it's just seeing gravity without, if you're measuring this intense gravity without being able to see anything, it sounds like you're measuring a black hole, right?
Well, with a black hole, things would be rather different. Because with a black hole, we have a different way of looking at orbits and things and whatnot. But there are galaxies like this. So when you look inside these galaxies,
that's another thing that I don't know anyone on the planet other than probably astrophysicists that know that there are galaxies that are 99% dark matter. So when you look at them, it looks like there's really nothing going on, but their gravitational pull looks like there's a lot going on.
Right.
Wow.
And and again, this is why I said that it's very hard to explain this by the other part with the alternative theories, because you would have to fit the theory to say, okay, for these galaxies, we have this way of calculating forces and acceleration and mass and velocity. For this one, we have another way of doing that, Well, again, for this type of galaxies, this is why it's like red flag to call dark matter. The baryonic processes, when you have so little normal or ordinary matter, cannot be countable for what you measure. You can't say, well, in these galaxies, everything that's ordinary creates this, but in these galaxies, wow, it creates 10 times more trouble.
Right.
So there are many things now, like a list of things where cold dark matter simulation doesn't fit the picture.
So could it be that, I'm sure this has been theorized, it would be the most logical, I would imagine, that in some galaxies, we know that matter, warps space, which creates the gravitational pull. So maybe there's just ripples in some galaxies that just have ripples for the sake of ripples rather than needing mass to burn, to bend that space. And maybe it's happening right here and we just don't know it. Is there anyone who looked at it through that lens that's saying that yes, mass creates gravity by bending space, but maybe there's just ripples in space anyway? Something as simple as that.
Right. So this would actually mean that the structure of space-time is not homogeneous to begin with.
Right.
That there's an underlying structure of something. And in some corners, things fall a certain way, and in other things, they just float in a different way in terms of gravity. Except this is not really supported by the way the observation look when you look in all the directions.
So maybe God is just laughing at us. Oh, this is the point I wanted to make. I had that question about CERN, and now I have a point. Oftentimes people go to a place and say, I've seen trees or green grass that was so green or so rich, and it seemed like that was reality. And that, to me, makes me think of simulation theory, that somehow the real reality is there, and this reality does its best. And I believe the Gnostics have this idea too, at the demiurge, the craftsman of the universe, try to freeze our soul into, I know I'm talking philosophically here now, right? But they tried to freeze our soul or trick our soul into thinking this is reality, so the demiurge can keep us imprisoned in this form. right? To keep the Sophia, the spirit of Sophia here stuck on the planet, or try to trap it here, right? And that when we realize who we really are, we go past this simulation and we go into the real spirit, where things they don't have duality, they don't have the illusion of separation. It's just these beautiful colors and the real grass, you know what I mean? Real trees, real, and these are just digital representations. Because every time it sticks in my head how much people say this. Like, I'm thinking to myself, why would, when you die, your occipital lobe would become more active and more excited and more, I know you could get a rush of dopamine and all this stuff that happens to the brain in order to endogenous endorphins in order to deal with death. But it's just over and over again, especially the guy with meningitis. That's what really woke me up to the possibility that maybe, just maybe, that's what we're doing. We're freeing ourselves for a moment from the simulation, going into the real world.
Well, this is something that was, again, one interpretation of this was with many indigenous populations that believe that this is actually the dream. And when they dream, that is the reality. So I'm not sure how much of this is escapism, trying to evade this reality as much as possible by denying its realness, because it's in many cultures and it's in many philosophies, the religions, if you want, the hints towards that. But in terms of the simulation theory, again, there are people looking at hints now. Like there was this article in, I think it was the New Scientist. Someone was saying, well, if it was made by programmers, they would have left an artifact, because any programmer does leave an artifact in the program. But that's, again, see the projection. We think as we think. So we're trying to project the way we program things now,
right,
to a whatever programmer above or below or behind or wherever, doing the exact same thing, but somehow smarter and with a better computer and for a purpose that we think we understand or not. In terms of, again, the dark matter, I don't know, again, if I were to think as a programmer, I would be thinking is like, okay, I got bored with creating all these small things that do all this kind of stuff, and just trying to hit the deadline, throw in like 85% of something that's called dark matter to make sense of the other 50, you know. But that's not an argument for anything, you know. That's just a projection of why the things would be like this if they were designed with this purpose in mind, to have us play in a simulation. The other thing in dogma, on the other hand, in science is, and where things get a little bit interesting from the programming point of view, is when you're simulating dark matter. Because, as I said, the dark matter, the cold dark matter doesn't fit. This is ignored. This is ignored. This is thrown, hidden under the rug. People would still claim that there's consensus and the majority think that the cold dark matter is the best model, and completely ignore or negate all evidence that it's not. Now, on one hand, this is also because there have been millions, if not billions, of the three major currencies invested in detecting this type of particles, the cold ones. And nothing was happening there. And the limits of the detection are basically now saying we're close to eliminating this as a particle candidate. For cold dark matter, for neutrinos, for axions, and so on. So I'm not saying that people who build detectors and people who try to make it in the lab, because CERN was trying to make it in the lab. So CERN was like, okay, if we can't detect it and we can't observe it, and let's try and make it in a lab by knocking off some other particles. And that was not successful as well. So on one hand, it's like the world's most expensive way of learning how not to make a light bulb, or its darkest alternative. I don't know what's the darkest, the opposite of a light bulb. But you know what I'm trying to say is like we learn how not to do dark matter in a very expensive manner. It's also, there were adjacent discoveries, like the Higgs boson, for example. There were other things that we understood and learned. But again, when you're talking millions and billions of dollars to just say it's not there, we should look somewhere else, it's a hard thing. And it's a matter of funding, and it's also a matter of behavior.
We should have another podcast on another episode of the Higgs boson, right?
Right.
Because they called it the God particle just to get attention, but it really has nothing to do with the God particles, basically, right?
Right. So
Higgs boson, right? Yeah.
So to show you exactly how bad it is in terms of like how bad people are trapped in their cold dark matter dogma, one of the other models that was catching on is warm dark matter. And again, between all those energies that I said, there are many shades of warmness in the warm dark matter. In the kilo electron volt range, there are simulations and then semi-analytical predictions that may explain what we see at the level of galaxies. Now, the catch here is that warm dark matter is more complicated than cold dark matter. It has some other properties that one would say, oh, that's an improvement. Except, again, all come forbid, we would have complications in science. People are very reluctant in accepting this. Cold dark matter is very simple, especially for programmers to program. If the universe was made such to be easy for programmers, that would be cold dark matter. Warm dark matter has all these different aspects of it, and all these, again, complications and the complexity that comes with it, that the simulations that we do are rough copies of what warm dark matter would be able to do. Nevertheless, even with the rough replicas that we have in simulations, we're still showing that there are points that are better than the cold dark matter. And this comes the cognitive dissonance. People are many papers that show this. Like people would say, this is cold dark matter plus baryons. This is warm dark matter alone. As you can see, cold dark matter plus baryons does better than warm dark matter alone. Then so the warm dark matter model must be wrong. Even you, without knowing much exactly about those things, realize that it's not like comparing the same thing here, right? You're comparing one dark matter with a different dark matter, and you just add a couple of things here, and you say, well, sorry. That's just one example. The same thing, we're going to add this cool thing to this theory. We're just not going to add it to warm dark matter, even though it's intrinsic for warm dark matter. And we're just going to say, oh, this just does better. Or we're simply going to say, well, it does better, but it doesn't solve all our problems. So in the end, we're just going to stick with what we know, which is cold dark matter, because it's so much easier. So this has been going on for so many years, and so many results have been misinterpreted in literature in order to just give this idea, to perpetuate this idea that warm dark matter is actually not doing well. It's constrained from all different things, and it's basically ruled out by the simulations and the observations. And it's simply not wrong. It's just a very unscientific way of being stuck in dogmatic view. Now, there is one experiment that shows that's promising here, and it's done by a group in Princeton. It's called the Ptolemy experiment, and it's the first one that's actually
What's it
trying
called?
to Ptolemy.
Colony?
Ptolemy, like the Greek.
Oh, Ptolemy. Okay.
Yeah. And that's where I would put my money, like right now. That's
What are they finding?
a particle in the kilo electron volt range for dark matter. Like if it's a particle, that's where I would put my money. Unless is a model that none of us thought of.
What do you mean? It's a particle in what range?
Kilo electron volt.
So are you saying it's, why would that not emit light or not reflect light or not block light?
No, it's a particle like the dark matter, but the energy at which it is produced is not going to be like mega electron volt, which is the heavy cold dark matter. Like neutrino, for example, it's the one that we know, the one that we measured, is in the milli electron volt.
Okay.
That's the energy of the particle, the energy to mass correspondence of the particle. So
Gotcha.
this would be in the kilo electron volt. Because if it would be lighter, it wouldn't form galaxies in the first place.
It's heavier. It's heavier.
Yes, but not heavy as to have the same problems as cold dark matter.
Got it. It's heavier as far as more energy to attract, more kinesthetic. Not kinesthetic.
More
kinetic.
pull, basically. It will
Pull.
More gravitational pull to form galaxies at the beginning. But again, it's a field that's plagued by dogma and by hidden agendas and double standards and all that, unfortunately.
Wow, this has been enlightening.
Pun intended, right?
This has got me up into the kilovolts range. Yeah, it's been fun. I think we should explore a little dark energy on our next podcast. What do you think?
Yeah, I'm all about the dark side, so.
I know you're cool. Well, thank you for joining us today. Thank you so much for all your insights. Would you tell us where to find your book again?
So, my book is titled The Dark Side of the Universe, and you can find it on Amazon. It's part of the Unexplained Rapid Reads collection.
Great. Look forward to reading it again now that we've had this talk. I think I'll understand it now. Thank you.
I hope so too. And if you have new insights, again, it may be something that no physicist has ever thought of. So bring them on. I'm open to hearing them.
Okay. Well, I've got my theory. I believe it's all poppycock nonsense.
I mean, that could be very fun to see.
Yeah, it just seems like that's what I was saying earlier. It seems like the more we learn, the more we look either out there or in there, right? The more the laws start to kind of get distorted. I'm wondering if there's maybe the theory of everything is some kind of bridge between the macro and the micro, right? Maybe there's some kind of bridge that bridge, the theories that belong to that bridge create a continuum from the nothingness into the something and into the all that is. And maybe there's some kind of math that puts it all together.
Well, as I said, just for the fun of it, and just because I'm all against the whole Occam's razor approach to science, it may just be that it's a combination of factors that comes into explaining the dark matter. That is not just one approach. It may just be a combination of factors, a little bit of our understanding, a little bit of the modification of a gravity force, a little bit of a particle here, and another one, just for the sake of complicating things for physicists. I would have so much fun with watching that unfold. And one more thing that I would like to add, again, for his dark materials fan. I've heard this vehiculated within the New Age, if I can say so, communities, that dark matter may be the consciousness matter, the matter for consciousness. hate to break it, hate to break it to them, and to again the fans of his dark materials. As much as I would love to have dark matter talk to me in angel voices, that's not plausible, because when you think about it, it's the most boring type of matter that you can think of. You think of the processes in the brain that are related to consciousness, and you have electrical things and chemical things and all those things that dark matter is not able to provide, because it doesn't have anything to do with the electrical field, the magnetic field. It cannot be connected with chemical properties because we're not even there in terms of the chemistry. So, sorry to say, but dark matter is the least likely candidate for any consciousness fields,
Got it.
unless
Cool.
it's part of the simulation theory. And then again, all bets are off.
Okay, great. That sums it up for today. Thank you. It was really cool. Great. Let's talk about dark energy on the next one.